What if the flap of a butterfly's wings in one part of the world could trigger a hurricane on the other side? What if the same mathematics that describe the weather could also explain how your brain thinks, how traffic flows, or how economies evolve? Welcome to Nonlinear Dynamics and Complexity Theory, the physics of unpredictability, patterns, and emergence. You're watching the Learning Studio, and in today's episode from our physics playlist, we'll uncover how chaos is not just disorder, it's a hidden order we're only beginning to understand. You can watch the entire physics playlist by clicking the link below in the description. This topic belongs to our new section Physics of Information, Life, and Complex Systems, where we explore how the laws of physics help us understand intelligence, life, and the world's most intricate systems. When linear thinking breaks down. For centuries, physics was built on linear models, equations where cause and effect were simple and proportional. Double the force, and you double the motion. Increase the energy, and the system responds predictably. But the real world rarely behaves so neatly. Weather, ecosystems, traffic, the stock market, they all change in ways that are irregular, sensitive, and interconnected. Here, small causes can have enormous consequences. That's where nonlinear dynamics comes in. It studies systems where a tiny input can create an unpredictable, sometimes explosive output. This sensitivity to initial conditions is what we call chaos, not randomness, but unpredictable order. It's why meteorologists can predict tomorrow's weather but not next month's. And why a single neuron firing can lead to thought, memory, or even emotion. Chaos, the hidden order behind unpredictability. When people hear chaos, they think of disorder, but in physics, chaos has structure. It's the dance of deterministic systems that never repeat but never truly randomize. The famous Lorentz attractor, discovered by meteorologist Edward Lorenz, revealed that chaotic systems trace beautiful, infinite loops in phase space, patterns that never intersect yet never vanish. This showed that even chaos has geometry. Nonlinear dynamics helps us understand weather systems, population cycles, heart rhythms, and even brain activity. And at its heart lies a profound truth. Nature's complexity doesn't come from randomness, it comes from interaction. Complexity theory, when many become one. Now, imagine taking nonlinear dynamics and scaling it up to millions, or billions, of interacting parts. That's complexity theory. It studies how simple local interactions lead to global order, how ants build colonies, how neurons form thoughts, or how markets self-regulate. These systems are called complex adaptive systems because they evolve, learn, and adapt without a central controller. Complexity theory connects physics with biology, sociology, computation, and even artificial intelligence. It's the language of emergence, how collective intelligence arises from individual components. From chaos to computation, AI and nonlinear systems. Today, AI and machine learning are transforming how we study complex systems. Instead of solving equations one by one, AI can learn the hidden patterns within chaotic data. Neural networks are being trained to model weather systems, predicting extreme events more accurately than traditional methods. Biological networks, from protein folding to brain connectivity, are now simulated using nonlinear models. Even economic and social systems are analyzed using complexity-inspired AI to forecast trends and crises. In return, physics borrows from AI too, using complexity theory to design algorithms that mimic nature's efficiency and adaptability. This beautiful exchange between physics and information science is reshaping how we think about intelligence, both natural and artificial. Why complexity matters. Nonlinear dynamics and complexity theory remind us that the universe isn't a static machine, it's a living network of interactions. It teaches us to see the hidden connections between simple rules and complex behavior. From predicting weather and preventing power grid failures, to decoding biological systems and creating resilient AI, this field offers us a way to understand, and even guide, the flow of complexity in our world. In essence, chaos is not our enemy, it's nature's creative engine. It's the source of diversity, adaptability, and evolution itself. This is the Learning Studio, and this was our episode on nonlinear dynamics and complexity theory. If you enjoyed exploring how chaos and order coexist in nature, make sure to subscribe, like, and check out our physics playlist linked below. In our next episode, we'll dive into biophysics and complex systems, where physics meets life, and where molecules, energy, and information unite to create living matter. Because in physics, even in chaos, there's a pattern, and within that pattern lies the story of everything.